Okay. Linear Algebra Lecture 2, and one of the homework problems, which had a typo in it that I corrected, is to solve this one linear equation, 2x minus 8y minus 6z equals 0. It's homogeneous because the right-hand side is 0, and we want to find the solution space. The solution space is all vectors x, y, z, and R3 that solve the equation. So if we have the equation 2x minus 8y minus 6z equals 0, let's say we want to solve for x, we can simplify a little bit by dividing by 2. So we have x minus 4y minus 6z equals 0. Or for any y and z, x has to be 4y plus 6z. So we have x, y, z is in the solution space W, if and only if x is 4y plus 6z for any y and z. So this is 4y plus 6z, yz. And for any y and z, this vector will be a solution, which we can write as, if we separate out the parts that have a y, 4y, y, 0, plus 6z, 0z. You add these two vectors, this is what you get. And this is simply y times the vector 4, 1, 0, and this is z times the vector 6, 0, 1. So the solution space W is a set of all linear combinations of the vectors 4, 1, 0 and 6, 0, 1. Oh, sorry, I made a mistake. If I divide by 2, I get x minus 4y minus 3z equals 0. So x is 4y plus 3z. That's a 3. For any y and z real numbers. So this is the subspace of R3 generated by or spanned by the vectors 4, 1, 0 and 3, 0, 1. So the proper form of the solution of this problem is that the solutions of this linear equation, one equation in 3 variables, is this subspace. This is the subspace of R3. It's all linear combinations of 2 vectors. Okay. Any questions about that? So that's basically what we did yesterday. We studied one linear equation. And today we're going to consider systems of 2 or more linear equations. So if we look at systems of linear equations. So an example of a system of linear equations is, so this is an example. 3x plus 2y equals 18. 4x plus 3y equals minus 5. So a solution is a vector xy in R2 that solves both equations. And for example, xy equals 64 minus 87 is a solution. So if you have a piece of paper in a few minutes, if you let x equal 64 and y equal minus 87, and you plug it in, you should get a solution. Let's just check. This is always important to check. If we take 3 times 64 plus 2 times minus 87. 3 times 64 is 192 minus 2 times 87 is 174, and that difference is 18. So that checks. If you look at the second equation, 4 times 64 plus 3 times minus 87. 4 times 64 is 256. 3 times 87 is 240, 261. And the difference is minus 5. So that also checks. So that's good. That's a solution of the system of equations. Now, the general form of a system of equations is the following. Recall, if you have just one linear equation, a1x1 plus a2x2 up to an xn equals b, there is the zero equation, which is kind of the trivial case. The zero equation is all of the coefficients, a1, a2, an are all equal to 0. And in that case, this equation has a solution if b is 0, and it has no solution if b is different from 0. If you have a non-zero equation, in the non-zero equation, j is different from 0 for some j, and then there is always a solution, because you can solve for xj and you solve the equation. Now, the situation with the system is a little bit different. So the general system, let's say m equations in n variables. So the first equation is, let's say, a11x1 plus a12x2 plus a13x3 up to a1n xn equals b1. That's the first equation. The next equation we normally write is a21x1, a22x2, a23x3 up to a2n xn equals b2, all the way down to the last equation, which is the mth equation, am1x1 plus am2x2, am3x3 up to amn xn equals b sub m. So this is a system of m equations in n variables. And the system is non-zero if at least one of the coefficients, aij, is different from 0 for some pair I and j. If every coefficient is 0, then you just have a set of 0 equations and it has a solution precisely when all the b's are 0. So it's only a non-zero systems that have that are of interest. Now, a system is consistent if it has a solution. A system is inconsistent if it has no solution. So, for example, the first set of two equations and two unknowns that we looked at is consistent because here's a solution. On the other hand, if we take the system of equations x plus y equals 0, x plus y equals 1, this system is inconsistent. There's no solution. Because x plus y equals 0, x plus y equals 1 can't happen simultaneously. 0 is different from 1. So not every system of equations has a solution. Some systems are inconsistent, and we have to keep that in mind. This system of equations is called homogeneous if all of the b's, the right-hand sides, are equal to 0. And inhomogeneous otherwise. So if at least one of the numbers on the right-hand side of these equations is non-zero, it's an inhomogeneous system. For a homogeneous system, if all of these numbers are 0, then you can let all the x's equal 0 and you have a solution. That's the zero solution or the trivial solution. And the non-trivial solution of a homogeneous system is a solution where not all the x's are 0. So all of this is written down in our chapter. Okay. And completely analogous to the results that we had for just one equation are the following. So this is in the notes. Theorem 5, the solution space of a homogeneous system is a subspace of Rn. So again, before we have our homogeneous system, we have equations in n variables. And homogeneous means the right-hand sides are all 0. So suppose x and y are solutions of the solution space W. So suppose x1 up to xn and y1 to yn are in W. So what does this mean? It means for every equation, for all I from 1 up to m, because they're m equations, we have ai1x1 plus ai2x2 up to ainxn is 0, and ai1y1 plus ai2y2 plus ainyn is 0. But if you add these equations, you get ai1 x1 plus y1 and so forth up to ain xn plus yn equals 0, which means the vector x1 plus y1 to xn plus yn, that's also in W. If we call this vector x and this vector y, that means that x plus y is in W. And if we take this equation and multiply it by c, you get c times 0, which is 0, which means cx1 down to cxn, which is c times the vector x, is also in W. And you have to remember what is the definition of a subspace. It's a set of vectors that contains 0. The 0 vector solves the homogeneous equation always, and is closed under vector addition and scalar multiplication. So that's the proof. And what about an inhomogeneous system? If you have just one equation, the solution space is a subspace if the equation is homogeneous, and an affine subspace if the equation is not homogeneous. Let me just recall the definition. So we have W is a subspace of the vector space Rn if the zero vectors in W. Second condition is that whenever x and y are in W, then x plus y is in W. And whenever x is in W and c is a scalar, c times x is in W. That's the definition of a subspace. And L is an affine subspace if L is, let's call it the translate of a subspace W. That is, there's a subspace W and a vector V, so L is V plus W. This means the set of all vectors V plus W, where W is in the subspace W. So you have a subspace W, and to every vector in that subspace, you add this fixed vector V. So you've translated the subspace by the vector V, and that's what an affine subspace is. So for example, if W is the set of all vectors x and y, such that x plus y equals 0, which is the same as the set of all vectors x minus x, x in R, or the set of all scalar multiples of the vector 1 minus 1, x in R. What does W look like? It's just the line x plus y equals 0 is y equals minus x. So in the plane, this is the subspace W. And suppose I let L be, let's say, 1, 0 plus W. Oops, let me write this properly. Let's say 1, 1 plus W. So this is the point with coordinates 1, 1. And what is 1, 1 plus W? That's the set of all vectors of the form 1, 1 plus x minus x. This is something in W, and we're translating it by 1, 1. This is the set of all vectors 1 plus x, 1 minus x, x in R. What does that look like? Well, let's see. If we let so if we let u equal 1 plus x and v equal 1 minus x, so 1 minus x is 2 minus 1 plus x by arithmetic, right? 2 minus 1 is 1. That's 2 minus u. So this is the set of all vectors where for any u, the second coordinate is 2 minus u. Or if you prefer, x is the set of all vectors x, 2 minus x, x in R. So y is 2 minus x. What is that? That's the equation of the line. This is line with slope minus 1 and y-intercept 2. Just a parallel line. So an affine in R2, a one-dimensional subspace is a line through the origin, And the translates, the affine subspaces are all lines parallel to that. So this is a nice example to keep in mind what an affine subspace is. And so suppose we take an inhomogeneous system. That is consistent. That means it has at least one solution. So we have A11 x1 up to A1 xn equals B1. We have m equations AM1 x1 up to AMN xn equals B sub m. So these are m equations in n variables, x1 up to xn. And let L be the solution space. So the fact that this is consistent means L contains at least one vector. So suppose V, V1 to Vn, is in L. That means for every one of these equations, AI1V1 plus AI2V2 up to AINVN equals B sub I for all I from 1 up to m. Let W be in, let's call it capital W, which is the solution space for the corresponding homogeneous system. It is, you look at the homogeneous system of equations, the left-hand sides are the same, but the right-hand signs are all zero. So one can check, and this is written out in the notes, that a vector V is in L if and only if V plus W is in L for all W that are solutions of the homogeneous system. And then it turns out, fortunately in this class, there aren't going to be proofs on the exams in any substantial way, that L is V plus W. The solution space of the inhomogeneous system is a translate of the solution space of the homogeneous system, where you translate by any particular solution of the system, of the inhomogeneous system. So just as in the case of one linear equation, when you deal with systems of equations, the solutions of the homogeneous system form a subspace, and the solutions of a consistent inhomogeneous system form an affine subspace. But the question is, how do you solve a system of equations? So, problem. How to solve, let's say, efficiently, or if you like, quickly, or easily, a system. So this is not as easy as it is in the case of one equation where you simply pick a variable and solve for it and you're done. Here we have a lot of variables, but also a lot of equations. So the idea is the following. You have a system of equations, and you want to, in some sense, simplify it. You want to get another system that has the same solutions, but it's easier to solve. So this requires a very important definition two systems of equations are in n variables are equivalent if they have exactly the same solutions. And it's then natural to ask, what can you do to a system of equations to get another system that's equivalent to the original system? So I'm going to list three elementary operations on a system of equations that produce equivalent systems. So again, keep in mind you have the system of equations, a11 x1 to a1n xn equals b1, a21 x1 up to a2n xn equals b2, down to am1 x1 up to amn xn equals b7. So what are elementary operations on a system that produces equivalent systems? So the first is very simple. You can interchange two equations. That is, this is the first equation, this is the second. If I interchange the equations, so I get a system where this is now the first, and this is now the second, it's exactly the same set of equations, just in a different order. So both systems have the same solutions. So this is interchange. You can always interchange two equations. What's another operation that's very simple that you can do? You can always multiply any equation by a non-zero number, non-zero scalar. That is, if I take this equation and multiply it by 5, if multiply through by 5, solutions of this equation are the same as the solutions of the equation without 5, right? I mean, if you want to solve x plus 2y equals 3, or 5x plus 10y equals 15, these have the same solutions. All I did is multiply by 5. So I can take any equation and multiply it by a non-zero number, and you get an equivalent system of equations. So that's kind of obvious. So this is multiplication. And the third, I'll call it replacement, is when you add so we choose one equation in the system and add to it a non-zero multiple of another equation. So let me just give an example of this. So suppose I have three equations and two unknowns. 4x plus 11y equals 115. X plus 7y equals 67. 8x minus 5y equals minus 13. So if I interchange the first two equations, I would get x plus 7y equals 67. 4x plus 11y equals 115. 8x minus 5y equals minus 13. So if I compare these two systems, all I did was interchange the first two equations. But the solutions of this system are exactly the same as the solutions of this system because they're the same equations, just in a different order. Now, I could also change this system by doing nothing to the second and third equations, but multiply the first equation, let's say, by 3. So I would get 3x plus 21y equals 201. So here I just multiplied one equation by the number 3, but it doesn't change the solutions. Any solution of this is a solution of this. Any solution of this is a solution of that. And then the last example, which is a little bit trickier, suppose I add minus 2 times the second equation to the third equation. So my first equation is still 3x plus 21y equals 201. My second equation is still 4x plus 11y equals 115. But then I add minus 2 times this to this. So minus 2 times 4x is 8x. When I add them, minus 8x plus 8x is 0x. Minus 2 times 11 is minus 22. Minus 5 is minus 27y. Minus 2 times this is minus 230. Minus 13 is minus 243. So when I add minus 2 times the second equation to the third, these don't change, but I get this new equation. And each of these operations is reversible. If I interchange two equations, if I interchange those same two equations again, I'm back where I started. If I multiply one equation by 3, then I get this. If I multiply this equation by 1 over 3, as if I divide by 3, I get back to this. And if I add 2 times this equation to this and get this, I can recover the original system by adding, here I added minus 2 times this, add 2 times this to this, and I'll get this back. Get this back. So each of these operations is reversible, invertible, if you like. So these are 3 operations that you can do to a system of equations to get an equivalent system. But you have to, at any time, many choices of what to do. How do you decide which of these operations to perform? And a strategy for doing that, one strategy, which is very important, classical, is called Gaussian elimination. So Gaussian elimination tells us what to do to solve a system of equations, to solve a system of linear equations. And maybe the best way to show what to do is just to start with an example. So let's look at these. There were several examples, and by seeing the examples, you'll know what it is you're supposed to do. So this is example 1. Suppose we have 9x plus 11y equals minus 1, and 5x plus 6y equals 3. So the first thing to do is, let's see, x occurs with a non-zero coefficient here. It's easier if the coefficient of x is 1. So I just divide this equation by 9, or if you like, multiply it by 1/9. So I don't do anything to the second equation. But the first equation, if I multiply by 1/9, I get x plus 11/9y equals minus 1/9. And then I want to get rid of the x in the second equation. So I have my first equation. And you can add a multiple of one equation to another. So I add a multiple of minus 5 times the first equation to the second. Or in the same, or another way of saying that is subtract 5 times the first equation from the second. So 5x minus 5x is 0x. Here I have 6y minus, well, let me just say this is like, let me write it out over here. If I take this equation and multiply it by 5, I get 5x plus 55/9y equals minus 5/9. And the second equation is 5x plus 6y equals 3. If I multiply this by minus 5, this would actually be minus 5 minus plus. And now I add these equations. 5x minus 5x is 0. 6 minus 55/9. 6 is the same as 54/9. So this is minus 1/9y. 3 is the same as 27/9. When I add, I get 32/9. So my second equation becomes minus 1/9 y equals 32/9. Now in this equation, I want the coefficient of y to be 1. So I have my first equation. If I multiply this by minus 9, I get y equals minus 32. So again, this system of equations has the same solutions as this system, and this system. I want to eliminate the y in the first equation. So I leave my second equation alone, but I add minus 11/9y to the first equation. So I have x plus 11/9y equals minus 1/9. If I multiply this equation by minus 11/9, I get 11/9 times 32, which I think is 352/9. If I add, these cancel, I get x equals minus 1/9 plus 352/9, which is 351/9. And 9 goes into this exactly 29 times, I think. Is that right? 3 into 37 is 3 is 27, 8, 29. So I get, 39. 9 to 35 is 39. So this system of equations is the same as this system of equations, but this is the solution. So we get the solution, the vector xy equal to 39 minus 32. And it should be, if you check, if you plug these numbers into this system of equations, you'll see that it works. So the strategy is to eliminate variables one by one. And as you go from left to right, from one equation to the next, the first non-zero variable in one equation is further to the right than the first non-zero variable in the previous equation. So this is an example of Gaussian elimination. Let me do another example. Here we have two equations. So this is example 2. We have two equations and 3 variables. 2x plus 3y plus z equals 1. 5x plus y minus 4z equals minus 1. So what do we do? Well, the first thing we want to do, so the non-zero variables in both equations are x. In the first equation, I want the coefficient of x to be 1, so I divide this equation by 2. I divide by 2, I get x plus 3 halves y plus 1 half z equals a half. And the second equation is 5x plus y minus 4z equals minus 1. Then I want to eliminate the 5x. So I subtract 5 times the first equation from the second. So the first equation doesn't change here. X plus 3 halves y plus a half z equals a half. If I subtract the 5 times the first equation from the second, I get 5x minus 5x is 0. I get 1 minus 15 halves. 1 minus 15 halves is minus 13 halves. Now, you have to do arithmetic to pass linear algebra, so that's just the way it is. Minus 4 minus 5 halves is minus 13 halves z, and minus 1 minus 5 halves is minus 7 halves. So in 2 steps, I have a system of equations equivalent to the original system, has the same solutions, but I've eliminated the x. Then in the second equation, I want the coefficient of y to be 1. So I have to multiply by the reciprocal of this, minus 2 over 13. So I have x plus 3 halves y plus a half z equals a half. If I multiply by minus 2 over 13, I get y plus z equals 7 over 13. Okay. Then I want to eliminate this 3 halves. So the second equation isn't changing, but I take the first equation minus 3 halves times the second. So x minus 0 is x. 3 halves minus 3 halves is 0. 1 half minus 3 halves is minus z equals, and then I have 1 half minus 3 halves of 7 over 13. 1 half minus 3 halves 7 over 13 is 1 half minus 21 over 26, which is 13 over 26 minus 21 over 26, which is minus 8 over 26, which is minus 4 over 13. So this system of equations, let me just write it down neatly, is x minus z equals minus 4 over 13, y plus z equals 7 over 13. In other words, for any number z, x has to be minus 4 over 13 plus z, and y has to be 7 over 13 minus z. So the general solution of this equation, x, y, z, is what? X is minus 4 over 13 plus z, 7 over 13 minus z, z, which is the same as minus 4 over 13, 7 over 13, 0, plus z minus z, z, which is minus 4 over 13, 7 over 13, 0, plus z times the vector 1 minus 1, 1. So the solution space is the affine space L equal to the vector minus 4 over 13, 7 over 13, 0, plus the set of all scalar multiples of the vector 1 minus 1, 1. For z, any scalar, z. Let's do another example. If this works for any number of equations and any number of variables, so this is the third example. In this case, we have two linear equations and four variables. You want to find all solutions. So x plus y plus z plus w equals 10. X minus y plus z minus w equals minus 2. Find all solutions. By the way, what happens if the solution is if the system is inconsistent? You'll get an equivalent system of equations, which will then sort of, when you look at a C, is unsolvable, has no solution, so you know the system is inconsistent. Here you can actually see that there is a solution. So if I let x and z be equal to 2, and y and w be equal to 3, I get 2 plus 3 plus 2 plus 3 is 10. 2 minus 3 plus 2 minus 3 is minus 2. So this is actually a solution. So we know this system is consistent before we start. Okay. So here we have this system of equations. The first variable we see with the non-zero coefficient is an x, but already has a 1. So the first step would just be to eliminate x from the second equation by subtracting the first equation from the second. So the first equation doesn't change. But when we subtract equation 1 from equation 2, x minus x is 0, y minus y is minus 2y, z minus z is 0, minus w is minus 2w, minus 2 minus 10 is minus 12. So that's an equivalent system. Now, here I have a y is the first variable that appears in the second equation. I want the coefficient of y to be 1, so I just divide the second equation by -2. The first equation hasn't changed. If I divide by -2, I get y plus w equals 6. Then I want to eliminate the y from the first equation. So I have y plus w equals 6 is the second equation. If I subtract the second equation from the first, I get x, the y's cancel, plus z, the w's cancel. 10 minus 6 equals 4. So I look at this, I can say, well, x is going to be equal to 4 minus z, and y is going to be 6 minus w. So if I choose any values for z and w and define x and y by these equations, I get a solution. So x, y, z, w, the general solution, x is 4 minus z, y is 6 minus w, z is z, and w is w. I can write that as 4600 plus minus z 0 z 0 plus 0 minus w 0 w. You'll see if I add them up, gives me exactly this. This is 4600 plus z times the vector minus 1010 plus w times the vector 0 minus 1 0 1. So my solution space is the affine space L equal to the vector 4600, which is a solution, particular solution to the original system of equations, plus the set of all scalar multiples of the vectors minus 1010 plus 0 minus 101 for all z and w, any scalars, any real numbers. That's what that says. So this is Gaussian elimination. And this you have to learn by doing. And the more examples you do, the more homework problems you solve, the more you will understand, or not understand, will understand, and also be able to implement this method of Gaussian elimination to solve a system of linear equations. Okay. This is really very important. So you know with 100% certainty that on the exam, the midterm exam, there will be a problem where you have to solve a system of equations by Gaussian elimination. A lot of them. Okay. Now, I want to prove the very important theorem that we apply over and over again when we're studying vector spaces. And that has to do with a homogeneous system of equations. So suppose we have a homogeneous system, A11x1, A12x2, up to A1n equals 0. A21x1 plus A22x2 plus A2n equals 0. all the way down to am1x1 plus am2x2 plus amnxn equals 0. So the theorem says if m is less than n, or if n is bigger than m, if n is bigger than m, so that means the number of variables is greater than the number of equations. N variables, m equations. If you have more variables than equations, then the homogeneous system, this is a homogeneous system of linear equations because the right-hand sides are all 0, has a non-trivial, which is the same as non-zero solution. If the system is homogeneous, then you can see if you let the trivial solution is when you let all of the variables equal 0. You just get 0 equals 0. In a non-trivial solution, x of j is different from 0 for at least one of the variables j. And there always is a trivial solution, a 0 solution to a homogeneous system. But if you have more variables than equations, there's always a non-trivial solution. And I'm going to prove this theorem right now. So the proof will be by mathematical induction. So let me explain this. And in course materials, there is a section, a chapter, if you like, called sets, relations, functions, which describes mathematical induction. But mathematical induction says the following. If a statement, some statement, or a proposition or assertion, whatever you want to call it, P of m is true for m equal 1. So when let m equal 1, the statement is true. And if whenever P of m is true, that implies P of m plus 1 is true. Then P of m is true for all positive integers m. And why is that? Well, P of 1 is true. And this says that for any number m, if P of m is true, P of m plus 1 is true. So if P of 1 is true, P of 2 is true. If let m equal 2, P of 2 is true, P of 3 is true. If let m equal 3, P of 3 true implies P of 4 true, and so on forever. So if you can prove that a certain statement which involves a variable m is true for m equal 1, and whenever it's true for m, it's true for the next number, next integer, m plus 1, then it's true for all positive integers. So that is a very important method for proving results in mathematics. It's called the principle of mathematical induction, and that's what we're going to use here. So first we have to prove the proposition for m equal 1. So m equal 1 and n bigger than 1, right? Because m is less than n is bigger than n, means we have an equation a11x1 plus a12x2 plus a1xn equals 0. this is an equation in at least, n is bigger than 1, it means n is at least 2. It's an equation in at least 2 variables. And I claim that this one equation has a non-zero solution. Well, if A11 equals 0, then if I let x1 equal any number 1, and all the other numbers equal 0, this is a non-trivial solution. This is 0, so 0 times 1 is 0. And all the other x's are 0, so you get 0 plus 0 equals 0. So if A11 is 0, then x1 equal 1, and all the other variables be 0, but at least one of the variables is non-zero. So that's a non-trivial solution. And if A11 is not 0, then you can solve for x1. You get x1 is minus a2 over a1 x2 minus a1n over a1 xn. And you choose any values for x2 up to xn. There's at least one variable here, if there are at least 2 variables. Define x1 by this formula, and you have a non-trivial solution. So the theorem is true when you have m equal 1 equations. Let's look at the case m equal 2. In this case, we have 2 equations, a11x1, a12x2, up to a1n xn equals 0, and a21x1, a22x2, up to a2n xn equals 0, and n is bigger than m, which is 2. In other words, m is strictly bigger than 2, n is at least 3. So we have 2 equations and at least 3 variables. So the first case is sort of the trivial case. If these first 2 coefficients are 0, if a11 equals a21 equals 0, then you can let x1 equal any number you like, 1, and the other variables all equal to 0, and you get 0 plus 0 equals 0. That's a non-trivial solution. In case 2, they're not both 0, so at least one of them is not 0. If this is 0 and this is non-zero, just interchange the solution. So in the second case, you can assume that a11 is not 0. So this is not 0. A21 might be 0 or maybe not. If it's not 0, you can eliminate x1 from the second equation by Gaussian elimination. Just subtract a multiple of the first equation from the second to get rid of x1. So now your system of equations looks like a11x1 plus a12x2 up to a1n xn equals 0. In the second equation, there's no x1 variable. You do have a22 called prime x2 up to a2n prime xn equals 0. So the system of equations looks like this. And this equation has, it's one equation, and how many variables? You got rid of x1, but this is an equation in n minus 1 variables, x2 up to xn, which is at least 2 because n is at least 3. So this equation has a non-trivial solution. So second equation has a non-trivial solution, x2 to xn. Plug those numbers into the first equation. A11 is different from 0, so you can choose x1 such that this is 0. Now, you need to think about this at some length, perhaps. That's the proof of this theorem when you have two equations and at least 3 variables. And now to prove the general case, which is the inductive step, that m be at least 3 and n is strictly bigger than m. So we have our system of equations, a11x1, a12x2, a1n xn equals 0, a21x1 plus a22x2 plus a2n xn equals 0, and so forth, down to the nth equation. Now, look at these leading coefficients in each equation. So if they're all equal to 0, if ai1 equals 0 for all I going from 1 up to m, just as before, you can let x1 equal 1 because these terms are 0, and everything else equals 0, and you have a non-trivial solution. So this is the easy case if all these are equal to 0. If at least one of them is non-zero, you can interchange the equations. So a11 is not 0. And then by subtracting suitable multiples of the first equation, from the other n-1 equations, we can eliminate x1. So we get a system of equations, and we can also divide by a11 to make it 1. So we get a system of equations equivalent to the original system. It looks like x1 plus a12 prime x2 up to a1n prime xn equals 0. a22 prime x2 up to a2n prime xn equals 0. Down to am2 prime x2 up to amn prime xn equals 0. So we have, again, m equations and n variables, homogeneous, but except in the first equation, there's no x1. Now, if you look at these equations, what we have here is m-1 equations in n-1 variables, homogeneous. And n bigger than m means n-1 is bigger than m-1. So these equations, so this system has a non-trivial solution. So you can find numbers x2 up to xn, not all zero, that solve these m minus one equations. And then you take those values of x2 up to xn, plug it in here, that x1 be the negative of this, so you choose x1 so this is 0, and now we have a non-trivial solution for the whole system of m equations and n unknowns. And if you study this for a while and think about it, and if you still have a question, come to one of our problem sessions at 7 o'clock every night and ask me for help. You've proved the theorem. And we'll see later on in the course how important this result is. So it says, again, if you have a homogeneous system of equations, m equations and n variables, if there are more variables than equations, there's a non-trivial solution to the homogeneous system. Okay. Good. And from our point of view now, this is the end of chapter 1. So tonight I will post chapter 2, but I'm going to start to talk about it right now. So we've been looking at equations, linear equations, but the subject of chapter 2 is matrices. And what is a matrix? So an m by n matrix. So m and n are positive integers. An m by n matrix is a rectangular array of scalars. A11, A12 up to A1n, A21, A22, A2n, down to AM1, AM2 up to AMN. You can say that this looks like the coefficients and when you have m equations and n unknowns, and we'll see tomorrow that is really a very precise analogy. So, for example, if I take A to be 1, 2, 3, 4, 5, 6, 7, 8, there are 2 rows, there are 4 columns. This is a 2 by 4 matrix. If I let B be 1, 2, 3, 4, 5, 6, there are 3 rows and 2 columns. That's a 3 by 2 matrix. If I let C equal 1, 2, 3, 4, 5, 6, 7, 8, 9, this is a 3 by 3 matrix. And for a matrix, we say the matrix is rectangular if the number of rows is different from the number of columns, and a square matrix if the number of rows equals the number of columns. So this 3 by 3 matrix is square, and these 2 matrices are rectangular. There's a very special square matrix, which is the identity matrix. IN is the n by n identity matrix. This is the matrix, let's see, with 1s down the main diagonal and 0s everywhere else. So let's see. I1 is just 1. It's a 1 by 1 matrix, just a number. I2 is a 2 by 2 matrix, 1, 0, 0, 1. I3 is a 3 by 3 matrix, 1, 0, 0, 0, 1, 0, 0, 0, 1. See, if you start at the upper left-hand corner and just go down, over one and down one, over one and down one, this sequence of numbers is called the main diagonal. I4 is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So down this main diagonal in the identity matrix, you have ones, and everything else is a zero. That's the identity matrix. It's a square matrix. There's a very important function called the Kronecker delta, delta ij. This is defined to be 1 if I equals j, and 0 if I is different from j. So, for example, I2 could be written as delta 1, 1, delta 1, 2, delta 2, 1, delta 2, 2. Where the I and j, the subscripts are the same, you have a 1. Where they're different, you have a 0. Or I3 could be written as delta 1, 1, delta 1, 2, delta 1, 3, delta 2, 1, delta 2, 2, delta 2, 3, delta 3, 1, delta 3, 2, delta 3, 3. Where the subscripts are the same, you have 1s. Everywhere else, you have 0s. So in general, In is the matrix where the ijth coefficient, or the ijth coordinate, is the Kronecker delta. Now, this is an important function to learn because we're going to use it all the time. And there's also the zero matrix, ZMN, is the matrix where everything is 0. So, for example, Z23, this is a 2 by 3 matrix, 2 rows, 3 columns. That's the 2 by 3 0 matrix. So we're going to spend a lot of time in this course working with matrices. An n-dimensional column vector. This is a matrix with one column. This is an M by 1 matrix. The first number is the number of rows. The second number is the number of columns. Here you have M rows, 1 column. Well, we can call an n-dimensional n, I'll call this M, an n-dimensional row vector x1, x2, up to xn. This is a matrix with 1 row and n columns. This is a 1 by n matrix. So from this point of view, a vector is just a very special case of a matrix. Now, there's an algebra of matrices of the same shape. So addition of m by n matrices is coordinate-wise. Let me just give an example. If I have the matrix 1, 2, minus 5, 0, 3, 11, that's a 2 by 3 matrix. When I want to add them, I just add coordinate-wise. 1 plus 5, 2 plus 1, minus 5 plus 4, 0 minus 2, 3 minus 1, 11 plus 7, So this is 6, 3 minus 1 minus 2, 2, 18. So I have the sum of two matrices, and it's defined just by adding their coordinates. And you can subtract matrices by subtracting their coordinates. So 1 minus 5, 2 minus 1, minus 5 minus 4, 0 minus minus 2, 3 minus minus 1, 11 minus minus 11 minus 7. That's subtraction. And I can multiply a matrix by a scalar. So that's scalar multiplication. So like I say, if I take the matrix 1, 2, minus 5, 0, 3, 11, if I multiply it by the scalar 7, I just multiply every coordinate by 7. 7 times 1, 7 times 2, 7 times minus 5, 7 times 0, 7 times 3, 7 times 11. So we can add matrices of the same shape. We cannot add matrices of a different shape. And matrix addition and scalar multiplication satisfy all the properties you want addition to satisfy. So matrix addition, so only adding matrices of the same shape. If you have matrices A, B, and C, you can add A plus B and add C to that. Or you can add A to the sum of B plus C, and you always get the same thing. So the word for that is associative. Matrix addition is associative. If you add A and B, you get the same thing as adding B and A. So matrix addition is commutative. If you take, so this is addition of n by n matrices. If you take an n by n matrix and add the 0 matrix, you just get back A. And if we define minus A to be the matrix you get by multiplying A by minus 1, so it's minus A, 1, 1. So just the negative of all the coefficients. A plus minus A is 0. Right? So, for example, if you take 2, 1 minus 7, 3, 0, minus 3, 0, 2, and you add the negative of this, minus 2 minus 1, 7, 3, 0 minus 2, everything cancels, you get 0. So this is A, this is minus A. And all these properties are straightforward to check. And similar properties are true for scalar multiplication of matrices. If you take a matrix A, multiply it by a scalar C prime, and multiply that by the scalar C, that's the same as first multiplying C and C prime and multiplying A. And you also have distributivity of that form and this. So if you let M sub little mn of R be the set of all m by n matrices, this is a vector space in the sense that you can add matrices and do scalar multiplication, everything works nice. Okay. We don't know how to multiply vectors, but this will be what we start by doing tomorrow. Multiplication of matrices. And what we'll see then, if we have A and B, if A is an M by N matrix and B is an N by P matrix, you can multiply them and you get a product C, which is an M by P matrix. So for matrix multiplication, you can multiply matrices A and B if the number of columns of A is the number of rows of B. So that's what we'll do tomorrow. Okay, good. It is summer school. We're moving along. We have to move rapidly because we have to cover a month's work in the first 4 days. And we are on schedule. So Wednesday and Thursday, we'll be going through the chapter on matrices, which will be posted this evening on Blackboard. Okay, well, I'm available as always, 7 o'clock at night, every night for questions. Otherwise, I'll be back tomorrow morning at 9.